Good day, everybody. In today's lecture, we are going to have a simple AC circuit, part 2 equation. Previously, we have discussed simple AC circuits, part 1 equation. So that is how the topic is being modeled. Now, in simple AC circuit, part 2 equation, we are going to look into equations of the inductor connected in an AC circuit and the capacitor connected in an AC circuit. Now let us see a case where we have AC circuits containing only inductor. A case where we have AC circuit containing only inductor, that is so this is a AC circuit containing only inductor. So this is the inductor here. And we have, this is the source voltage. And this is the current, this is the frequency. And this is a symbol for AC. So the voltage across the inductor is given as L di dt. So this is L di dt, where I is given as I naught sine omega t. That is the value for current. So by the time I substitute this into this equation, I'm going to have this will give me m d dt into I naught sine omega t. Already I naught is a constant, then I'll factor it out. If I do that, I'm going to have I naught m d dt of sine omega t. Now, differentiating this sine omega t, that is going to give me omega L I naught cos omega t. I'll call this equation 1. Then this remains my equation 1. Then from trigonometric identity, cos omega t is given as sine omega t plus pi over 2. That is from trigonometric identity. So by the time I substitute, wherever I see cos omega t here, I will substitute sine omega t plus pi over 2. And if I do that, I will have this. This is omega L I naught sine omega t plus pi over 2. So that is what it gives. Then I call this one equation 2. I can call this equation 2. I will now say, but omega L I naught is equal to V naught. Call this equation 3. V naught is the peak voltage and this is the peak current. Substituting this into this place, I will have Vm will give me V naught sine into omega t plus pi over 2. I call this equation 4. This is my equation 4. Then I will have recall from equation 2. Okay, recall from equation 3 that omega L I naught is equal to V naught. This can also be expressed as omega L is equal to V naught over I naught. This can be expressed as this. Then I'll call this equation 5, where W omega L is equal to XL. That is inductive reactance. I call this equation 6. So I will substitute this into this place. That will give me inductive reactance is V naught over I naught. Call this equation 7. Recall that V naught is equal to voltage root mean square root 2, and I naught is given as current root mean square root 2. I call this equation 8. Then I'm going to substitute this equation 8 into equation 7. If I do that, I will generate another equation, which is in this form. Then when I substitute this into this, I will have this to give me voltage root mean square root 2 over current root mean square root 2. You know, root 2 we cancel root 2. You now have this as voltage root mean square over current root mean square. Generally, inductive reactance will give us omega L, which is equal to voltage root mean square over current root mean square. They call this equation 9. This equation is equation for inductive reactance. That is for this equation, and this inductive reactance is measured in ohms. Then we look into the current flowing in the circuit. The current flowing in this circuit is given as current root mean square is voltage root mean square over this, over inductive reactance. Then wherever, okay, we can have this. This is called equation 10. This one is formula for current flowing in the circuits. That's the formula for current flowing. Then energy stored in an inductor. The energy stored in an inductor is given as energy stored in an inductor will give us half Li square. This I is current root mean square. I call this equation 11. This one is the current flowing. This is the energy stored in an inductor. Then we can also calculate the inductance of an inductor. The inductance of an inductor can be generated from this equation, given that XL is equal to WL. L here is inductance of an inductor and is measured in Henry. So I can make this L the subject of the formula. If I do that, I will have XL over W omega. And this omega is given as 2 pi F. So I will have this over 2 pi F. So this formula is equation 12, and this is formula for inductance of an inductor. Okay. So for instance, if your resistor, you have resistors connected in series, then you can have the effective resistor, if you have inductance connected in series, then the effective inductance is given us, if you have these ones are connected in series, you have L1, L2. So the effective, which is the equivalent or the total, will give you L1 plus L2 in case this one is connected in a circuit. So that is how this one is being modeled. I've just designed the equations for inductor connected in an AC circuit. Then I'm going to look into the capacitor connected in an AC circuit. Let me show you this. Only capacitor connected in an AC circuit. Now I have AC circuits containing only capacitor. AC circuit containing only capacitor is designed like this. The circuit is designed like this. You have the capacitor, you have the current, you have this. Then I have voltage root mean square and frequency. This is the ampere. You have the current root mean square. Then this is your C. Then there's a voltage across this. This is the circuit for capacitor only connected in an AC circuit. Now the voltage across the capacitor is given as 1 over C integral of I dt. This is the voltage where I is I naught sine omega t. By the time I substitute this into this equation, I'm going to have Vc equal to 1 over C integral of I naught sine omega t dt. Then this one is a constant, it will come out. I will have Vc equal to I naught over C integral of sine omega t dt. Then by the time I integrate this, I'm going to have this. If I integrate this one, I'm going to have Vc is equal to I naught over omega C into negative cos omega t. Integration of this is this. Where negative cos omega t is given as sine of omega t minus pi over 2. So wherever I see this one, I'll substitute this into this equation. So Vc will give me I naught over omega c sine omega t minus pi over 2. This is a very wonderful equation. So this is a wonderful equation where I naught over omega c, I naught over omega c is V naught. Call this equation 1 and call this equation 2. So this equation 2 can also be rearranged in this form. I can have this equation like this, 1 over omega c to be equal to V naught over I naught. Call this equation 3. This is equation 3. And in this equation 3, 1 over omega c is Xc. Call this equation 4. X means capacitive reactance. So capacitive reactance is given as 1 over omega c. So I can put this one into this place. I will now have Xc is equal to V naught over I naught. Call this equation 5. This is equation 5. We also recall, we're going to recall that peak voltage and peak current are given as, peak voltage is given as voltage root mean square root 2. Peak current is given as current root mean square root 2. Substitute this into this place. You can say, call this equation 6. Substituting equation 6 into equation 5 will give me Xc to give me voltage root mean square root 2 over current root mean square root 2. Root 2 will cancel root 2. That gives me voltage root mean square over current root mean square. So the general formula for capacitive reactance is given as this. This is equal to 1 over omega c, which is equal to voltage root mean square over current root mean square. This is the general formula for capacitive reactance. And this capacitive reactance is measured in ohms. So let me see the capacitance of a capacitor from here. See, here is the capacitance of a capacitor, which is measured in farads. So let me make see the subject of the formula, and that will give me the formula for capacitance of a capacitor. Let's see how it goes. Okay, now from this one, or I can say from here to here, or I can say from here to here, depending on my choice or the nature of the question. So if I choose this place, I'm going to have Xc to give me 1 over omega c. I want to make c the subject. That will give me c equal to 1 over omega xc. So already you know where omega is 2 pi f. By the time we substitute this into this, this gives me 1 over 2 pi f xc. Call this equation 8. This equation 8 is equation for capacitance of a capacitor and is measured in farad. Knowing fully that 1 farad, 1 microfarad, sorry, 1 microfarad, 1 microfarad is equal to 10 raised to the power of negative 6 farads. So this one is the formula for that. We also have energy stored in a capacitor. The energy stored in a capacitor is given as this. The energy stored in a capacitor. Energy stored in a capacitor is given as half CV square. And this V is voltage root mean square. Now take for instance, this one can call this equation 9. This one is the energy stored in a capacitor. But if your capacitor is connected in series or your capacitor is connected in parallel, let us just demonstrate a little thing. Yeah. If we have this, let's say your capacitor is connected in parallel like this. You have a parallel connection of capacitor like this. This is a capacitor. And I have C1, C2. If your capacitor is connected in parallel, the result of this is going to be addition. So effective capacitor is going to be C1 plus C2. But if it is connected in series, if your capacitor is connected in series like this, maybe C1, C2, the effective capacitor will give you, we say product over sum, meaning this times this, that is C1 times C2 over C1 plus C2. So this is when your capacitor is connected in series and when your capacitor is connected in parallel. This one can also be given as 1 over C effective, which is 1 over C1 plus 1 over C2. So these are the equations for simple AC circuit part 2 equation. So we're going to in the next class, we are going to use these equations and solve calculation, and that one will be simple AC circuit part 2 calculation. As this one is simple AC circuit part 2 equation, we're going to use the equations we've derived so far and solve a lot of calculations in the next class. Thank you and remain blessed.